Welcome to Columbia Physics Preceptor Television. Today I will be demonstrating an introduction for the conservation of momentum experiment. Conservation of momentum is a physical principle that dictates how bodies act when they undergo collisions or explosions. We know from lecture that momentum can be written as the product of a body's mass times its velocity. You'll notice that momentum is a vector quantity. This means that, like forces, it has to be added using the tip-to-tail method, and also that it has both a magnitude and a direction. This will be important when we use it in calculations later on in the experiment. To observe conservation of momentum, we need to realize that its underlying principle is that in any physical process, whether it be a collision or an explosion, momentum is conserved. That is, the initial momentum is equal to the final momentum, both in magnitude and direction. This happens in all cases, not just inelastic or elastic collisions, but in all collisions. To observe this, we'll use two different apparatus. The first apparatus is a ballistic pendulum. This is simply a mass suspended by a pair of strings such that it can swing freely back and forth. What we will do is use an air gun to fire a small metal ball with mass little m and velocity little v at the can, such that it sticks into clay that's inside the can. The can will then observably swing back a certain distance. We would like to use this distance to be able to calculate the initial velocity v of the small ball. We can do this by observing a few different physical principles. First, conservation of momentum. This says that the initial momentum of the metal ball, little m times little v, is equal to the mass of the large can and the ball's combined system times their velocity right after the collision. We can observe that as the can swings back, it eventually comes to rest and then swings back down to an equilibrium position. As it comes towards the top of its swing, we can say that all of the can's kinetic energy from the bottom of the swing is now gravitational potential energy. We can write this as 1/2 times the mass of the system times the velocity squared is equal to the combined mass times the gravitational constant and a height h. Measuring h is very difficult since the can is only at its height h for a very small amount of time. However, we can observe that the strings of the can form a right triangle along with the horizontal, such that this distance h can also be related using the Pythagorean theorem to the distance d that the can moves back. We can equate this by saying that the length of the strings, r squared, is equal to r minus h squared. This is the length of the leg of the triangle when the can is at its highest position, plus d squared. We can rearrange this and substitute it into this equation for h. Also, we can combine these two equations to get a final form for the velocity as a function of the distance that the can has moved, d. Now, you should have done this before coming to lab, but in case you haven't, I'll give you the final answer. In this case, little v is equal to the sum of the masses over the original little mass times a square root I'm running out of board space. Given by this expression. Now, when doing the experiment, you should make sure to fire the metal ball twice. In its first swing backwards, the can actually loses a lot of energy to moving a small slider that you will use to measure d backwards along a ruler. There is friction between the slider and the ruler, and that friction saps the can of some of its energy. Also, if the clay starts to get stiff, you want to make sure to leave it under a sun lamp for a little amount of time, such that the ball will stick to the can when it's fired. So, our second apparatus to observe conservation of momentum will be using an air trough. and a pair of riders of different masses inside that air trough. This is a simpler situation in theory, and we'll be looking at two situations. The first is an elastic collision between two riders, and the second is an inelastic separation caused by detonating a small blasting cap between the two riders and seeing how they come apart. What we'd like to do is compare the velocities of the two riders before and after the collision and the explosion compared with theoretical values. In the elastic collision, we know that we start off one rider with a velocity v, and towards a stationary rider, the larger rider. When the two riders collide, they will then bounce off in opposite directions. You'd like to position the larger rider such that after this collision, the two riders hit the ends of the air track at the same time. This will allow us to equate the distance of that rider, or of the point of collision, from the ends of the air track. Call those distances S1 and S2. The ratio of those two quantities will be equal to the ratio of the velocities of the two riders. This may require a lot of careful positioning during each experiment. You may have to do each experiment a few times in order to get this spacing right, such that the riders hit the ends of the track at the same time. Now again, you should have derived the predicted values for V1 over V2 before coming to class, but I'll do them for you in case you haven't. For the elastic collision situation, we know two things about the collision. First, as always, momentum is conserved. We can say in this case, m1, the mass of the small rider, times its initial velocity, the initial momentum, will be equal to the final momentum. This is m1 times the final velocity v1 plus m2 times the final velocity v2. Also, because the collision is elastic, we can say that energy is conserved and simply write down the kinetic energy for the system before and after the collision. From these two equations, you can combine them and rearrange some terms to come out with a predicted value for V1 over V2, which in this case is the difference of the two masses divided by twice the small rider's mass. You can weigh the riders beforehand in order to get a sense for a predicted value for this ratio. In the second case, we'll be starting off with zero initial momentum, since the two riders are at rest and held together just very slightly by the piston containing the blasting cap. You'll then use the Tesla coil to detonate the blasting cap, sending the riders apart. Again, you would like the two riders to impact the ends of the air track at the same time, such that we can use this equation to get a measured value for the ratios of the velocities. However, in this case, we can only rely on conservation of momentum to predict our value for V1 over V2. So, for the inelastic case, it should be noted that this is for the elastic collision. For the inelastic case, we'll start off with zero initial momentum. The final momentum will simply be m1 v1 minus m2 v2. And I actually made a mistake in this equation. This should be a minus sign. This is illustrating how tricky it can be when dealing with momentum which have both a magnitude and a direction. Simply rearranging this very simply gives us the final result that v1 over v2 is just a ratio of the two masses. But in a slightly different order. v1 over v2 is m2 over m1. There are a few sources of uncertainty in this experiment. The main one will be the position of the riders initially, such that this condition is met. That is, the distances from the initial starting point of the collision is such that the riders impact the sides of the air track at the same time. The uncertainty in this measurement may not only be the granularity of the ruler. The riders may start to slide, your position may be slightly off, resulting in some non-simultaneity between the impacts, but you should estimate this for yourself and try to come up with a quantitative estimation for what the uncertainty due to that cause is. Also, you may want to do the experiment a few times in order to get this as close to perfect as you can. However, in terms of doing the actual experiment, you will have to estimate your uncertainties since there is no 2/3 method or best fit line method to get your final uncertainties. So that's about it. Have fun.